Good morning, everyone. My name is Jialuo, and today I'm going to talk about the durability of highly flowable self-healing concrete under freeze-thaw actions. And here's the table content. I'm going to begin with some background and the innovation of our study, and then I will go on with the experimental design and share some interesting results and findings with you. And finally, I will make some conclusions. So, as you know, the annual cost of maintenance and repair related to bridge alone in the US is about $5.2 billion. And when the cracks are not visible or accessible, the cost will become higher, and even the repair work will become impossible. The other thing is that the Urea-formaldehyde microcapsules with calcium nitrate as the healing agent has been proven to be a mature and promising self-healing technique for cementitious materials. However, its potential for enhancing freeze-thaw durability of concrete has rarely been studied yet so far. So we investigate the freeze-thaw durability and predict the service life of this self-healing concrete by using the Weibull distribution model. And also we propose the methodology of distinguishing the air voids, microcracks, and the Urea-formaldehydes inside the self-healing concrete based on the 3D X-ray microcomputed tomography. So here's the mixture design of 4 groups of samples in our study. We have control samples, control plus PVA microfiber samples, 1% 700, 1% 350 plus PVA fibers. The number 700 and 350 are the Urea-formaldehyde microcapsules since that's under such agitation rate. And 1% indicates the adding dosage of the microcapsule by weight of cement. So they all have the same water cement ratio of 0.45, cement to sand ratio of 1 to 1.5, and sand to coarse aggregate ratio of 1 to 1.3. And here's the gradation of our coarse aggregate. Since it's highly flowable, so we tested the slump flow of the fresh concrete mixture, and they are both greater than 520 millimeter in the orthogonal directions, according to the ASTM of solid self-consolidating concrete. And we performed the tests on the concrete samples to rapid freeze-thaw test per ASTM C666. And here are the sample size with 3 by 4 by 16 inches. And on the right side, here's the test machine that we use to conduct the freeze-thaw cycles. And on the right corner, we have the instrument that we use to measure the relative dynamic modulus of elasticity over freeze-thaw cycles. So here's the results. The evolution of relative dynamic modulus over freeze-thaw cycles, as we can see here for control samples without the PVA fibers, they quickly failed after 81 freeze-thaw cycles and have barely 40% left of the original, the initial value of the relative dynamic modulus. However, for the self-healing concrete samples without the PVA fibers, even after 700 freeze-thaw cycles, the drop of relative dynamic modulus is only 5 to 10%. So we established some numerical relation between the relative dynamic modulus and the number of freeze-thaw cycles, along with 5% prediction interval limits. As we can see here, all the numerical relationships fits good with the test data. So I'm going to do some background introduction of the Weibull distribution model. It is a probabilistic damage analysis tool to predict the service life of concrete, which has been proven previously. And the probability density function for the 3-parameter Weibull distribution model is defined as this expression. And the alpha is the scale parameter, beta is the shape parameter, and the gamma is the location parameter, n is the number of Freeze-Thaw cycles. So by integrating the PDF, we can have the cumulative density function as follows. And we do some term switching and do the logarithm on the both sides. We can have the expression like this and do the logarithm again, and we can have this expression, which can be regarded as a linear expression here, which has a statistical parameter B and A. So these two statistical parameters could be obtained via the least square estimation, and the Bernard approximation is employed to obtain the median ranks for estimating the unreliability for each failure. So by estimating a corresponding value of gamma, we can obtain the value of A and B by applying the linear curve fitting. And also, we're going to use the reliability function in the future to do some prediction, which can be defined as 1 minus the cumulative probability function. And also, the failure rate function is defined as probability density function divided by the reliability function. And also, the damage variable, which is also known as the damage level, and the durability factor are related to the dynamic modulus of damage and intact samples. As we can see here, after 54 Freeze-Thaw cycles, the durability factor of control samples are barely over 60, while the self-healing concrete samples are still around 100. And even after 300 Freeze-Thaw cycles, the self-healing concrete with microcapsules alone dropped to like 85 or 86. And the samples with PVA fibers, the self-healing concrete samples with PVA fibers still around 100. And even after 732 cycles, the self-healing concrete samples still have a durability factor of over 80. So we're going to do the Bernard approximation for all these samples at different damage level of 0.1, 0.4, 0.6 for control sample, and 0.05, 0.1, and 0.4 for self-healing samples. By doing the linear curve fitting, we can have the expression so that we have the value of capital A and capital B. Then we can calculate the alpha, beta, gamma based on the expression I talked about previously. And then we plug the number of alpha, beta, and gamma into the function, and we can get the probabilistic density function here, as shown here. And we do the integration, so we get the cumulative probability density function. And then we can have the reliability function curves and the failure rate function curves. So based on the reliability function, we can do some estimation of the number of Freeze-Thaw cycles that concrete samples need to achieve a certain level, a certain damage level. As we can see here, the 95% reliability prediction makes the most conservative prediction here. And then we can compare our test data with the predicted data of 95% reliability, 50% reliability, and also the numerical equation that we developed at the first beginning. As we can see here, the 50% reliability prediction can do a better prediction than the 95% reliability. That's because the 95% reliability prediction is more conservative. And here's the reliability and prediction of self-healing concrete. So after 300 Freeze-Thaw cycles, we cut a cubic sample with a size of 1 by 1 by 1 inch and place it on the rotating stage to do the X-ray micro-CD. So we can obtain a series of 2D scanned slices, and we put the stacked 2D slices into the ImageJ software to do the analysis. And one important step of analysis in ImageJ is to do the threshold adjusting. So as we can see here, there are 3 peaks here. The first peak indicates the air voids. The second peak here indicates the concrete matrix. And the third shoulder-like peak indicates the coarse aggregate. And when we do the threshold adjusting, we should confirm whether we should stop. So here are the indications of air void, the void presentation situation with the increase of thresholding. As we can see here, with the number of threshold increasing from 10 to 20 to 30, there are more void showing, but only 20 is more close to the accurate situation. And here's the GIF I gave you. With the increase of the adjusted threshold, you can see that more and more dots are presenting in the slice. So we should choose a value at the very feet of the second peak to make sure that we didn't miss too many voids, and also not including too much irrelevant voids. So after we conduct the series, we can see that these are definitely entrapped air voids. And when we do some zooming, we can see that here's the crack propagating from one void to another. And I picked up some representative voids, and we can see here this is intact one. This is a small void with a little tail, which means the cracked. And this is a crack propagation, and this indicates 2 voids getting connected by the crack. So we need to distinguish based on a key parameter, whether it is circularity or roundness. As we can see here, this intact one has a roundness very close to 1, which means perfect. However, the circularity is much lower. And for these 2 cracked air voids, they should have a less value of roundness. However, the circularity give a higher value. So roundness is more accurate than circularity. This is because the expression here, the circularity is considers the parameter, but the roundness considers the major axis. So here's the size distribution of the air void system. We can see that the crack fraction is decreased with the addition of Urea-formaldehyde microcapsules. And here's the reconstructed pseudo 3D image. So we can see that the self-healing system consisting the microcapsules along or microcapsules with PVA fibers can significantly enhance its freeze-thaw durability. And also the Urea-formaldehyde microcapsules plays an important role, not only providing the healing agent, but also providing extra space for the volume expansion of liquid in concrete during freezing. But PVA seems to make limited contributions. And also, we can conclude that it is feasible to use Weibull distribution model to predict the remaining service life of self-healing concrete. And finally, we can say that the roundness is a key parameter for distinguishing the microcracks from air voids in concrete. So thank you very much. Any questions?
Let me ask you a question. What is the advantage of this method compared to other methods that are in the industry right now? What makes it so so relevant?
Yeah, because in this study we can see that I didn't add any air training agent in it. So the microcapsule, the added microcapsules can act as not only as a air training agent to provide more air in-train air voids, but also provide more provide healing agent to heal the microcracks after over the freeze-thaw cycles the concrete has been subjected to.
And also, I think this is a common question for such methods. How expensive is this?
So far, the synthesis process of this Urea-formaldehyde microcapsule is mature, and it has. So far I don't have the exact number of how much does it cost per ton or per kilogram, but I'm sure that the synthesis process of this microcapsule is mature and can be easily achieved in industry because it's in situ polymerization via water in oil.
Sure. And then one more question. How sustainable are these capsules compared to air training agents? Sustainable.
Yes, sure. So as we all know that with the addition of air training agent, the concrete can last longer for freeze-thaw cycles. But if the degree of saturation of the concrete itself is over like 88%, then the in-train air void will lose its effectiveness. So for the concrete with the embedment of microcapsules, it can last longer than the in-train air voids.
Okay.
I would say at least 5 to 10 years because it can survive for over 700 freeze-thaw cycles.
All right. Thank you. Thank you, Dr. He.